Dear friends, Maths Aspirants Groups organizes several online problem-solving sessions to help the students, those who prepare for competitive examinations like CSIR, NET-JRF, JAM examination, and other PG and Ph.D. entrance examinations. As a part of that programs, today we are having a problem-solving session on functions of several variables. For discussing that topic, we blessed to have an eminent scholar, Mr. Mahesh T V, who is a research scholar at Indian Institute of Space Science and Technology, IIST, Thiruvananthapuram. He has completed his PhD and submitted the thesis now. He qualified CSIR JRF in 2015 and he did M.Phil from Cochin University of Science and Technology and M.Sc from Pondicherry Central University. Mr. Mahesh last year also taken two problem solving sessions for our Math Aspirants Groups, and that sessions were students were really benefited out of that. All that sessions are now also available in our YouTube channel. Today he will discuss about more ideas on functions of several variables, as it is one of the hot topic for CSIR NET exam as well as JAM examination. I'm sure that his class will be really useful for those who are preparing for JAM, NET, GATE, etc. I would like to thank Mahesh for accepting our invitation to join with us, and I welcome all of you to this event. Hope that today's session will be really beneficial for all of you. Thank you everyone. Welcome, Mahesh.
Thank you for calling me once again. Today we will discuss some functions of several variables and some problems, previous year problems. Basically CSIR and GATE and JAM exams problems. Okay, so these are the two references I suggest: a course in multivariable calculus and analysis, Gropade and Limai. So those who are preparing for this type of competitive exam, this first book will be very useful. And the second one is also very standard book, a calculus on manifolds by Spivak. Okay. Let me begin with the limit and continuity. So I have already wrote all the basic definitions and its properties, so that it will be easier for us to recall all the basics, and we will directly go for the problem sections. So let me first define limit and continuity. So let us consider a function f from some D to R, where D is some open subset of R2. Usually we will take open subset of R2, and x0 and y0 are 2 points in x0, y0 is a point in D. Now first we recall what is the definition of limit xy tending to x0, y0 f of xy. So in single variable cases, if I am looking a function from R to R, then how we will define this limit? We have a line on there. You have a point some x0. So we wanted to look at limit x tending to x0 f of x. So there are two possibilities to approach this point. Either you can approach from left or from the right. So both the way you approach and you look at the limiting case, then if those two values are equal, then we define that equal value as the limit x tending to x0 f of x. So we denote those things by limit x tending to x0 plus f of x. The other one is limit x tending to x0 minus f of x. So if these two values are equal, then we say limit at x0 exists, and that is denoted by this one. Okay. The same way I will define this also, but if I am looking the points in the plane, so I am looking here for R2. So D is my domain, it is in the plane. So one point you can approach in a several manner. So along each curve you look at that, all the curve you look at passing through the point x0, y0. Along each curve you can approach this x0, y0 two ways, right? So we will look at all such possible curves and look at the limiting case along each curve. If all such values exist and all are equal, then we say that as the limit at x0, y0, and it is denoted by this symbol, this one. So what we have to do is we have to consider all the curve passing through x0, y0, and along each curve we will look at the limit. And if all those values are equal, and that equal value is defined as the limit at x0, y0, and it is denoted by this. Okay. So let us consider some example. So I wanted to check whether for this example the limit at 0, 0 exists or not. So this is a very standard example. So what we have to do is we have to consider all the curve passing through 0, 0, and whether the limit along each curve is same, it will be equal. So let us consider some curves passing through 0, 0. So this is the point 0, 0. And what I will look at is I will look at all the line passing through 0, 0. So you can generally take y equal to mx. M is the slope. If m varies, you will get a different curve. So I will consider the line y equal to mx, where m is the slope. So if you give m equal to 1, you will get y equal to x. If you give m equal to 2, you will get y equal to 2x. So those are the different curves passing through 0, 0. So along y equal to mx, if you look at the limit, what you will get? Limit xy tending to 0, 0 along y equal to mx. I am looking. So what you will get? In the numerator, you will get x into y is mx. So x into mx divided by x square plus m square x square. So numerator we have x square, denominator also we have x square, both term having x square, so that we can take outside. So it will be limit xy tending to 0, 0 along y equal to mx. X square you can take out, so it will be m divided by 1 plus m square. So since there is no x and y here, this value will be m by 1 plus m square. So what actually it means? So if you approach 0, 0 along the curve y equal to x, in that case m is 1, you will get the value 1 by 1 plus 1 by 2, right? If your m is 1, you will get the value 1 by 2. So if your m is 2, you will get the value 2 by 5. So different value you are getting along different curve. You are getting different value. They are not equal. So this limit at 0, 0 does not exist. So this quantity does not exist. So limit xy tending to 0, 0 f of xy does not exist. Does not exist. Okay. So what we did is we approach 0, 0 along different curves. So I consider a family of curve y equal to mx. So if m is different value, you will get different value. Okay. Now let us recall the definition of continuity. As in the same case of a single variable, limit xy tending to x0, y0, f of xy should be is equal to f of x0, y0. So f is said to be continuous at the point x0, y0 if this limit should exist and it should be equal to f of x0, y0. So this is the definition of continuity. Okay. Now there is a sequential definition. So that you might have seen in single variable case also. In generally, you can define it for matrix spaces. Here you consider a function f from D subset of R2 to R, and x0, y0 is a point in D. So we say f is continuous at x0, y0 if for any sequence x and yn converges to x0, y0, f of x and yn converges to f of x0, y0. So you consider any sequence x and yn converges to x0, y0 is that implies f of x and yn converges to f of x naught y naught, then f is continuous at x naught y naught. So then we say it is continuous on the domain means it should be continuous for every point in the domain. So the sequential definition. So let us look at the same example using this sequential criteria. So we have already seen this function is not continuous at 0, 0. So can you construct some sequence for 0, 0? Anyone? Can you construct some sequence for the point 0, 0 for this function? Anyone?
1 by n, 1 by n.
Sir,
Yeah,
1
yes,
by
fine.
n, 1 by n by
Yeah,
2
1 by,
by n.
yeah, 1 by n, 1 by n, 1 by n is fine. Or 1 by n, 2 by n is fine.
2 by n,
Okay.
yes.
Yeah. So you consider the sequence x and yn as 1 by n, 1 by n. Okay. Then we can easily observe that this 1 by n, 1 by n will converge to 0, 0. Then what about f of x and yn? F of x and yn is, you will get 1 by n square by 1 by n square plus 1 by n square. So it will be 1 by n square divided by 2 by n square. So you get 1 by 2. So it does not converge to, it is not going to f of 0, 0, right? So x and yn converges to 0, 0, but f of x and yn does not converge to f of 0, 0. So it is not continuous at 0, 0. So we will look at another example. This function f of xy is equal to x square y divided by x raised to 4 plus y square. For this example also we can see that this function is not continuous at 0, 0. For that you can consider the sequence x and yn as 1 by n, 1 by n square. If you take this sequence 1 by n, 1 by n square, you can easily observe that this x and yn converges to 0, 0. But what about f of x and yn? F of x and yn is 1 by n square, 1 by n square divided by 1 by n raised to 4 plus 1 by n raised to 4. So finally you will get 1 by 2 again. But it does not converge to f of 0, 0. Okay. So this function is also not continuous at 0, 0. Now let us look at the definition of uniform continuity. So anyway, we are talking everything in a matrix space. R2 is a matrix space with the usual metric, the Euclidean metric. So the uniform continuity is same as the uniform continuity on the matrix space. So I will give you a definition which connected to the sequence. So we say f from D subset of R2 to R is said to be uniformly continuous on D if for any sequence x and yn, sequences x and yn and a and bn, such that the norm of this value, this is actually the norm, Euclidean norm, norm distance is converges to 0, implies f of x and yn converges to f of x and yn minus f of a and bn converges to 0. So if you have to consider any sequences so that its difference goes to 0. For any sequences, their norm, this Euclidean distance converges to 0, then modulus of the f of x and yn and f of a and bn, that also goes to 0. If that implies, if this condition implies this one, then we say f is uniformly continuous on D. For any sequences, all such pairs you have to look at. Okay, let us look at some example. So you consider this function f from R2 to R defined by f of xy is equal to x plus y. So we can easily observe, see that this function is uniformly continuous. So let us start with some arbitrarily two sequences, xn and yn. Another sequence a and bn, such that their Euclidean distance converges. So this square root of xn minus an square plus yn minus bn square converges to 0. So I consider some sequence xn yn and an bn such that these things converges to 0. Now you can easily observe what is f of xn yn. That is xn plus yn, and f of an bn is an plus bn. So then I'll write it here. Then what happened to this modulus of f of xn yn minus f of an bn? That is in fact is equal to less than or equal to, you can use the triangle inequality, mod xn minus an plus mod yn minus bn. Again, this is less than or equal to, I can say this is less than or equal to this value, right? Square root of mod xn minus an square plus yn minus bn square. This one from here to here you can use in fact the norm relation. Norm of one norm is always less than or of that of two norm, right? This thing you might have seen in this matrix space theory. Norm 1 is less than or equal to norm 2. So using that, this quantity will converge to, since it is converges to 0, this also will converge to 0. So you can easily observe, I have taken two arbitrary sequences and I obtained the conditions. So this is a uniformly continuous one. Now look at another example. This is just analog of the 1 by x in single variable case. Let us look at the domain. Set of all xy belongs to R2, such that x and y are coming from the closed interval 0, 1 and x comma y not equal to 0, 0. So I am looking this square. This is my domain. This closed interval, this is 0, 1 and this is 1, 1. This is 0, 1 and this is 1, 0 and this is 0, 0, right? Okay, this is my domain and this point I am removing. This point is not in my domain. All other points are there. So this is the entire my domain except this point 0, 0. So now I look at the function f of xy is equal to 1 by x plus y. I wanted to say this function is not uniformly continuous on this domain. So it is just an analog of the function 1 by x on open interval 0 or closed interval 0, 1 or open 0 close to 1. You might have seen this function 1 by x. X belongs to open 0 close to 1 in single variable case. You can easily prove that this is not a uniformly continuous on single variable case. So it is just an analog of that one. So to see this is not a uniformly continuous, I will use this sequential definition. So I will consider two sequences so that its difference converges to 0, but f of x and yn and f minus f of a and bn does not converge to 0. Such a sequence I will construct. So let us look at this sequence xn yn, that is 1 by n comma 0. There is a first sequence I consider, and another sequence I consider a and bn as my 1 by n plus 1 comma 0. So you can easily observe that this square root of xn minus an square plus yn minus bn square, what you will get, this will be nothing but square root of 1 by n minus 1 by n plus 1 square, right? So this is in fact square root of 1 by n into n plus 1 square. So I can write it as 1 by n into n plus 1. So this converges to 0 as n tending to infinity. Okay. Now you look at f of x and yn. What you will get? F of x and yn. That is, you get n 1 by 1 1 over 1 by n plus 0. So that is n. And f of a and b n, what you will get? That is n plus 1. So what you will get the difference? The difference is f of x n y n minus f of a n b n. That will be 1. So it does not converge to 0. So you got a sequence. So that is difference goes to 0, but the f of the difference is not going to the 0. So this function is not uniformly continuous on this domain. So another example I will look at. This is the function f of xy is equal to x square plus y square. So you can easily check this. I have given a hint here. So I'm not going to prove these things. This is just an analog of f of x is equal to x square. So you might have seen f from r to r in single variable case, and f of x is equal to x square. You can easily prove that this is not uniformly continuous. Not uniformly continuous. So this function is just an analog of this one. So you can easily construct two sequences. I have given the hint here. This is the sequence. These two sequences you can take, and you can observe that the difference is going to 0, but f of the difference is not going to 0. So that is so you can easily do by using the sequential definition. You can easily prove that the given function is uniformly continuous. It will be helpful for you to prove that it is not uniformly continuous. So this definition is very helpful for showing that some function is not uniformly continuous. Okay. Now let us look at the definition of partial derivative. So you have a function f from D subset of R2 to R, and x0 y0 is a point in D. Now I will define two subset of R using this D. The first one is I will denote it by D1. That is all those points, all those x in R such that x comma y0 belongs to D. So it is basically the I have this x R2 and my point x0 to y0 is somewhere here. What I am having is I am looking all those x such that x comma y belongs to D, y0 belongs to D. So I look at this horizontal line, this line. So this line is given by, or this portion of this line on D, that is given by D1. So suppose this is my D, I will look at this much portion only. I won't consider full line. I will consider this much only. So whatever the corresponding domain. So you have to take the portion of this line in the domain. The other one, D2 is this line. I consider all those y so that x0 to y belongs to D. So all those y so that x0 y belongs to D. So this line is D2 and this line is D1. Now I define partial derivative of f at x0 y0. Suppose x0 is an interior point of D1. Suppose x0 is an interior point of this D1. Then we define partial derivative as this way. Dou f by dou x at x0 y0 is limit h tending to 0 f of x0 plus h minus f of x0 plus h comma y0 minus f of x0 y0 by h. So we consider only the increment in first variable. So with respect to x, that increment we are considering. That changes we are looking only with respect to x by fixing y as constant. So this is the partial derivative of x with respect to x. Partial derivative of f with respect to x at the point x0 y0. Similarly, if y0 is the interior point of D2, we can define the partial derivative that is denoted by this way, dou f by dou y at x0 y0, and it is defined as the limit h tending to 0 f of x0 y0 plus s minus f of x0 y0 by h. This is the partial derivative with respect to y at the point x0 y0. So there is another notation for the partial derivative. Usually we denote partial derivative by fx at x0 y0. Similarly, fy at x0 y0. This is another notation. So we are talking partial derivative at a point x0 y0. Now we have some important things to remember. So let us look at some examples. So the first example is very important. It says the continuous function need not have partial derivative. So I will consider a continuous function and I will show that the partial derivative does not exist. So continuity does not imply the existence of partial derivative. So as you have seen in single variable case, all continuous functions are not differentiable. So it is just analog of that theory or that result. Okay. Now look at this example. F of xy is equal to square root of x square plus y square. Yeah, this is the function. We can easily observe that this is a continuous function. This is a there is no problem for this function. This is very smooth function, right? Means in the continuous sense it is smooth. Root of x square plus y square. Yeah. Now I will show that this function is partial derivative at 0, 0 does not exist. So let us look at the partial derivative with respect to x. So I will look at this one, fx at 0, 0. What is that? By definition, it is limit h tending to 0, f of 0 plus h, 0 minus f of 0, 0 divided by h. So what is that? Limit h tending to 0, f of h0 by h. Right? F of 0, 0 is 0. If you put f of 0, 0 here, you will get 0. So f of 0, 0 is 0. So what is this quantity? This is limit h tending to 0, square root of h square by h. What is square root of h square? That is in fact mod h, right? Limitation 0 mod h by h. So if h is approaching from the right of 0, you will get to 1. If it is from the left of 0, you will get a -1, right? So you have 0 somewhere here. And if so, what actually it is getting? Limit 0 plus is in fact h by h, that is 1. And limit h tending to 0 minus is minus h by h, that you will get -1. So these two are not equal. So this limit does not exist. Does not exist. So it says the partial derivative at 0, 0 does not exist. Fx at 0, 0 does not exist. Similarly, you can prove fy at 0, 0 does not exist. There is nothing change. Only you have to write in with respect to the other variable. That's all. So both the partial derivative are not existing. Fx at 0, 0 and fy at 0, 0 does not exist. But you can easily observe that this function is a continuous function. So for the continuous, there are continuous functions in which the partial derivative does not exist. Now you look at the other side. So this is most important for this partial derivative case. So this is not there in the single variable case. Single variable case, all differentiable function are in fact continuous function, but this result is most important for partial derivative case. So existence of partial derivatives does not imply f is continuous. So there are functions in which the partial derivative exists, but it is not continuous. That is the most important thing. So let us look at that example. So this is a very most important result. This is the important result. Partial derivative should exist, but f is not continuous. Let us look at the example. This is the function f of xy is equal to xy by x square plus y square. So the same function what we have already seen. We have already seen that this function is not continuous. Now I will prove that both the partial derivative will exist at the point 0, 0. So let us look at this one. Fx at 0, 0. So what is that? Limit h tending to 0, f of 0 plus h, 0 minus f of 0, 0 divided by h. So what is this quantity? This is in fact, so you look at here, what is f of 0 plus h comma 0? So since the numerator contain both x and y, it will be 0, right? Y is 0 here. So f of h0 is 0 and f of 0, 0 is also 0. So this total thing is 0. So you get it is 0, right? So ultimately, finally you get this as 0. Similarly, you can see this fy of 0, 0. What is that? That is limit h tending to 0, f of 0 h minus f of 0, 0 by h. This also you will get 0 because f of 0 h is 0 because in the numerator of this function x is there. So x into something will become x is here 0, so it is totally 0. So both are you are getting as 0. So both the partial derivative exist, but we have already seen this function is not continuous. This is the first example we discussed. So this function is not continuous at a 0, 0. Not even the limit exists at a 0, 0, but both the partial derivative exist. So that is the beauty. You see, these functions at a 0, 0 limit does not exist, but its partial derivative exists. So the existence of partial derivative does not imply f is continuous. But in the single variable case, suppose f is differentiable, then it is automatically continuous. But in the case of two variable, for the partial derivative things, this result is very important. Now we will look at the definition of directional derivative. Yeah. So let us consider a function f from D subset of R2 to R, and x0, y0 is some point in D, and let U be some unit vector. Unit vector means its norm has to be 1. U1 square plus U2 square is 1. Now the directional derivative is defined by these equations. The directional derivative is denoted by du f at x0, y0, and it is defined by this way: limit t tending to 0 f of x0 plus tu minus f of x0 by. So I will tell you what actually these things. So we are considering some point in some vector. So far, in order to approach a point, suppose you wanted to approach the point x0, y0. It is somewhere here, right? Some point. You can approach this point in a different direction. So because this is in the plane, you can approach in infinitely many ways. So I will fix one direction. That is all. Suppose I fix this direction. That is my u1 and u1i plus u2j. That is my direct vector corresponding unit vector. So this point I can approach different direction, right? So I will fix one among the direction, and I am looking the derivative along that direction. That is actually the meaning of directional derivative at the point x0, y0. So suppose I am looking the directional derivative at x0, y0 in the direction of the standard vector. That is, suppose this is my point x0, y0. I can approach this point using the standard direction, right? So we say, what I will say, I will consider this line, and I will look at by this direction. This direction is in fact the same as that of 1, 0, right? This vector E1. This is the standard direction. So if I look at this standard direction, then I will get the partial derivative what we have already seen. So the directional derivative is actually means you can approach the point x0, y0 in a different direction. So we will fix some direction, that's all. So if the direction what we fixed is the standard vector direction, then it will turn out to be the partial derivative. So I will once again look at the definition. So this is the definition. You have to consider a unit vector u. The unit vector is enough to look at the direction. Why we wanted to concentrate on unit vector? Because suppose I consider some direction, like suppose for example 1, 0 I am looking. This is one direction. Again, if you get another vector like 2, 0, this is also in the same direction. See, these two vectors are in same direction, and if I compute the directional derivative for this direction, suppose I take this vector instead of 1 0, I will get one value. Again, if I take another vector, for example 3 0, again I will get another value. So for the same direction, I will get a different value as a directional derivative. So then the definition of directional derivative does not give a unique value. So you cannot. So the problem is that if you are not restricting on the unit vector, that definition does not make sense, right? So there is on the same direction you will get a different value. So it does not give a unique value. So the definition make problem. That is why we are always concentrating on the unit vector. So you have to consider a unit vector u, and then the directional derivative is defined by these equations. Okay, so this we can rewrite. Here it is the capital X0, that is X0 Y0. So here we can rewrite it as the way as the follows. So this is the definition you have to look at. So here the du of f of x0 y0 is limit t tending to 0. This is the small x0, x0 plus tu1 y0 plus tu2 minus f of x0 divided by t. So limit t tending to 0 we have to consider. This is the directional derivative of f at x0 y0 in the direction of u. Okay. So if you look at the directional derivative in the direction of the even vector, you will get the partial derivative with respect to x. If you look at it in the direction of E2 vector, you will get the partial derivative with respect to y. Okay, now let us look at one example. So you have to consider the directional derivative of f any direction. I am not fixing any direction. You can take some arbitrary direction. Okay, so you have to find this value. Let u be a unit vector. Now I will look at du of f at 0 0. What is that? Du f at 0 0. By definition, this is limit t tending to 0, f of 0 plus tu1, 0 plus tu2 minus f of 0 0 divided by t. Okay, then it will be limit t tending to 0, f of tu1 tu2 minus f of 0 0 by t. So you can compute f of tu1. So if you substitute here, what you will get, f of 0 0 is 0. So you have to substitute tu1 here. Then the numerator is limit t tending to 0. Numerator what you will get is t square u1 square t cube u1 u2, right? So you will get t cube u1 square u2, correct? Yeah. Then the denominator what you will get, divided by t is there, then here you will get t raised to 4 t raised to 4 u1 raised to 4 plus t square u2 square, right? Yeah. Now okay, you can pull t square outside. What you will get? It will be limit t tending to 0 t cube into u1 square u2 divided by t cube you can take outside. So this is t square u1 raised to 4 plus u2 square. So these t cube will cancel, and finally you will get u1 square u2 by u2 square. So it is finally yeah, u1 square by u2. So provided u2 has to be non-zero. u2 is non-zero. If u2 is equal to 0, what you will get? If u2 is 0, your tu2 will be 0, right? If u2 is 0, your this quantity tu2 will be 0. So this will be 0. If u2 is 0, this will be 0. Then if you substitute in this equation, you will get a 0 only, because the numerator x square y is there. So totally you will get a 0. So for u2 is equal to 0, you will get a 0. So if u2 not equal to 0, you will get a u1 square by u2. So your directional derivative is du f at 0, 0 is u1 square by u2 for u2 not equal to 0, and 0 for u2 is equal to 0. Okay. So this is the directional derivative. So here the directional derivative exists all direction. So all the directional derivative exists. So what you can say about this function? We have already seen this function. What observation we already made about this function?
Not continuous, sir.
Yeah, yes. This function is not continuous. This function is not continuous at 0, 0, but the directional derivative at 0, 0 exists in the all direction. Is that correct? So the directional derivative exists all direction, but the function is not continuous. So that is the observation. The function is not continuous, but all the directional derivative exist. Function is not continuous, but all directional derivative exist at 0, 0. So in order to exist the directional derivative, continuity is not needed. Continuity is not needed. Okay, now look at another example. So this is another example. This is also very, sorry, it's the same example we discussed, right? Okay. Okay. It is there, fine. Yeah. Okay. So this is the same example, I think. Yeah. Okay. Now look at another example. You can easily prove this. I'm not going to do this one. There exists a continuous function in which no directional derivative exists at some point. So this is the you can say the converse or not converse. It is just a contra of the previous thing what we have seen. So there are continuous functions in which no directional derivative exists at some point. This is the example. You can easily observe that this function is continuous. This function is continuous, and you can prove that the directional derivative does not exist in a direction at the point 0, 0. You can easily prove that this one du of f at 0, 0 does not exist in any direction u at the point 0, 0. So this function is continuous, but no directional derivative exists. So the previous one is this is the same one. The previous one is the function is not continuous, but all the directional derivative exists at 0, 0. So there is no connection from continuity and directional derivative. So if the function can be continuous, but directional derivative does not exist. So but function need not be continuous, but still the directional derivative can exist. So both cases, some functions are there. Okay. Now we look at the definition of derivative of a function. So let me. I think you might have seen this directional derivative in your smaller class. So there you might have written some formula like this: directional derivative du f at 0, 0 should be equal to del f at 0, 0 dot u. Okay, So this is the vector. You might have seen this in your previous classes or in the schools. Mostly in +2, so we are doing finding directional derivative, directly computing these things. But this is not in generally correct. You cannot write directional derivative as this way. In order to write this thing, you need extra conditions. Simply for a given function, this relation does not hold. So I will see when it will happen. I will discuss those things. Okay. So first we will look at the derivative of function of two variables. So far we discussed partial derivative and directional derivative. Now I will go for the definition of total derivative or the Fresher derivative. So let us first we look at the definition. Let f from D subset of R2 to R and x0 and y0 are point in x0 y0 is a point in D. We say f is differentiable at the point x0 y0 if there exists a pair alpha comma beta belongs to R2 such that this relation holds. That means f of x0 plus h f of y0 plus k minus f of x0 y0 minus alpha h minus beta k by norm of hk should be 0. If this happens, then we say f is differentiable at the point x0 y0. So suppose there exists some alpha beta satisfying these things. Okay, let us before going to details, I will just give a motivation for the definition. So we will begin with a single variable case. I just want to give you a motivation why this definition came. Okay, let us look at the function f from R to R. Okay, a single variable case, and all of you know what is the definition of f dash of x0. X0 is some point in R. So what is that? This is limit h tending to 0 f of x0 plus h minus f of x0 by h. This is the definition for f dash of x0. So basically what we are getting some real number. We have a geometrical interpretation. We will say it is a slope of the tangent at the point x0. So I'm not going for such details. So here what I am ultimately getting is a real number, right? F dash of x0 is a real number belongs to R. Okay. A derivative at a point x0. X0 is a point in R here. x0 is 0. Okay. Now I wanted to look at in a different way. What I am doing is I am trying to understand this as in a different manner. So I will look at all the linear transformation from R to R. What are all the linear transformation from R to R? All the linear maps. How the linear map from R to R look like?
Scalar multiple of identity.
Yeah, yes. So if I consider some linear map from R to R, it should be of the form T of x is equal to some lambda x, right? Where lambda belongs to R. Okay, so it's just a scalar multiple. Now, so every real number I can associate to a linear map, right? If you take a real number, I can have a linear map T. Now I am going to rewrite this equation. I'm going to rewrite this equation in terms of a linear map. How it is? I will write it here. Let us look at this. Limit h tending to 0 f of x0 plus h minus f of x0 by h is equal to f dash of x0. So this equation is same as to write this one, right? Limit h tending to 0 f of x0 plus h minus f of x0 minus f dash of x0 times h divided by h. So both are same, right? Equal to 0. So these two equations are same. Then this quantity I can look at it as some scalar times h, right? F dash of x0 is a scalar. So it is a scalar times h. So I will write it as this way. Limit h tending to 0 f of x0 plus h minus f of x0 minus some t of h divided by h. What is the t? T is the linear map T of x is equal to f dash of x naught times x. This is the linear map. T is from R to R linear. Okay. So this quantity I can look at it as with respect in terms of linear map. So this is the real motivation for looking the derivative from multivariable case as a linear map. So we will consider a function f from D subset of R2 to R. Now we will consider a function R2 to R. Okay. And I wanted to look at the derivative at a point x0 that is denoted by x0 y0. So this capital X0, I wanted to look at the derivative at that particular point. So using this observation, I will define the derivative as a linear map from R2 to R. So the derivative at a point capital X0 is a linear map. I say it is L from R2 to R. So this is the derivative. L is the derivative, linear map. So we will define the derivative as follows. If such L exists, if there exists a linear map L from R2 to R such that limit h tending to 0 f of capital X0 plus h minus f of x0 minus L of h divided by norm of h I have to take, because I am talking here in R2. This h is in fact a vector in R2. So I may take it as capital H if you have confusion. Okay, this is a vector in R2. The norm is the 2 norm, usual 2 norm. This happened to be 0. So if this happened to be 0, then we say, suppose there exists some L satisfying this relation, then we say f is differentiable at x0 and the derivative is this linear map L. Now you tell me what are the linear map from R2 to R, how it look like. So suppose you have a linear map from R2 to R, you can always go for the matrix, right? So the matrix of the linear map, how it look like? It is a 1/2 matrix, right? So it should be of the form some L of H should be of the form some alpha beta dot H, right? H, if you take H as H comma K, small h comma K, capital H is equal to small h comma K, you can precisely write it as alpha H plus beta K. Do you understand this? Hello?
Yes, sir.
Do you understand? Yes. Okay, so that is the way this definition arises. You see, here I have written alpha, there exists some alpha beta belongs to R2 satisfying this relation, right? So here alpha H minus beta K I have taken. So if you take a minus altogether out, you can return it as, simply you can write it as this way, right? Minus of, right? That will be nice. So here this alpha h plus beta k is in fact your L of h. Alpha h plus beta k is in fact your L of h. L is the corresponding linear deformation. So the linear deformation only coming here, this portion. And this square root of h square plus k square is nothing but the norm of h. Here the capital H norm I have taken. Norm in R2 only I am taking. So this is the capital norm. So this likewise you can define general map from Rn to Rm also. You can define the derivative using the transformation from Rn to Rm. So I am not going for that much higher dimensions. So this is the motivation behind this definition. So it comes from R to R only. So every derivative you can think as a linear map. Using that only this definition arises. Now we will see some important things to remember. Suppose f is differentiable at the point x0, y0. Then I have seen that this derivative is a linear map, and the corresponding linear using these vector alpha and beta, you can write from linear from R2 to R, it will be giving a 2 by 1 vector, 1 by 2 vector. And then the corresponding scalars alpha and beta you can compute. That will be this partial derivative. That should be of this one. So this is about getting using the standard basis. Suppose you have a linear transformation, you can find the matrix of the linear transformation using different bases. But if you look at the standard basis of R2 and find the matrix, you will in fact get alpha and beta as this quantity. Alpha is this and beta is this. So your derivative, if it is exist, alpha should be partial derivative with respect to x at x0 y0, and the beta should be partial derivative of y with respect to partial derivative of f with respect to y at x0 y0. And finally, you can write the derivative as this one, del f at x0 y0. If the function is differentiable, and if it is a function from R2 to R and it is differentiable at the point x0 y0, and then the derivative is denoted by this way. The derivative should at the point x0 y0 is gradient of f at del f at x0 y0. Now I will say some properties also. If f is differentiable at x0 y0, then we can easily prove that f is continuous at x0 y0. I'm not going for the proof of this one. And another one is, this is the important thing I wanted to point out. Suppose f is differentiable at x0 y0, then all directional derivative exists at x0 y0, and the directional derivative must be equal to this thing. So directional derivative du f at x0 y0 should be is equal to this. So I am not going to discuss. There is one example I have not included there, so that this is not equal. If someone is interested, you can go for the reference one. It is there. That example is there in the reference one. Reference one. Okay. So what actually it is saying is, so in order to guarantee this equality, f has to be differentiable at the point x0 y0. If it is not differentiable at x0 y0, this equality is not guaranteed. But still the directional derivative can exist, but you have to compute the directional derivative using definitions. You cannot simply write this equation and find in the directional derivative. That is not possible if the function is not differentiable. Okay. Now we will go for some sufficient condition for the derivative. We will go for the sufficient condition for the derivative. So we have a function f from D subset of R2 to R, BMF, such that both the partial derivative exist, fx and fy exist on some neighborhood of x0 y0 for some delta positive. If one of them is continuous at x0 y0, if either fx or fy, if one of them is continuous at x0 y0, then f is differentiable at x0 y0. So in order to guarantee the derivative, what you have to do is, you have to look, first you have to compute whether the partial derivative exists on the entire domain, or it means entire region like this, in these portions it should exist, and it has to be, one of them has to be continuous in this domain. Then f is differentiable at x0 y0. So one point I wanted to, one thing also I wanted to point out, if f is differentiable, here we have seen that all the directional derivative exist. So in particular, the partial derivative automatically exists. Suppose f is differentiable, then we have seen that all the directional derivative exist at x0 y0. So since the partial derivatives are a particular case of directional derivative, that also automatically exists. So the differentiability implies the existence of partial derivative, and the other side, simply if the partial derivative exists, we not guarantee that the function is differentiable. So in order to have the differentiability, this one of the partial derivative has to be continuous in small neighborhood of x0 y0 intersection D. In this region, it should be continuous. One of them has to be continuous. Okay. Now I will give some basic idea of maxima, minima, and saddle point. Then we will go for the problems. Okay, this is a single variable cases. Single variable cases, how we will look at maxima, minima. So we will go for a function and we will look at the derivative. If the derivative is 0, then we will again go for the points with the second derivative. If the second derivative is less than 0, that point is the maximum, right? If the second derivative is greater than 0, that point is the minimum. And there is another case called point at inflection. The point at inflection means the point from where the curve changes the concave to convex or convex to concave. For example, at the point B, this is concave that changes to convex, right? This point. And the D is the same type of point. So, but there f dash is 0, right? At the point D also f dash is 0. And B, at the point B, f dash is need not be 0. F dash is need not be 0. But there can be a point at inflection with the derivative 0 or not equal to 0. But the other cases, for finding the maximum, you have to go for the first derivative. If it is 0, then you go for the second derivative. If it is less than 0, that is the point of maximum. Here A is the point of maximum and C is the point of minimum. Okay. Now we will look at the analog of things to function of two variable. Let us look at that one. Now I have definition. What is a point is called a local maxima. So f has a local maxima at a point A comma B if this holds for every point xy in the neighborhood of AB. So you have to consider a neighborhood of the point AB, and at least one neighborhood should exist. This statement says at least one neighborhood should exist. So you look at the point A comma B, and there is a neighborhood such that this inequality hold f of A comma B greater than or equal to f of xy for every point xy in that neighborhood. Then we say A comma B is the local maximum. Similarly, there is a neighborhood so that f of A comma B less than or equal to f of xy. Then we say this is a point of local minimum. F has local minimum at A comma B. Now there is one more point called a saddle point. For the saddle point, what we have is that you look at the point A comma B, you consider every neighborhood. In these cases, you have to find at least one neighborhood satisfying these conditions. But if you look at for the saddle point, you have to consider every neighborhood of the point A comma B. Then if there exists point xy so that f of AB less than f of xy, and there are other points with the f of AB greater than f of xy in the same neighborhood, for all the neighborhood, if it is such a points exist, then such a point is called a saddle point. So you have to look at all the neighborhood of AB. There are points so that f of AB less than f of xy and f of AB greater than f of xy also. So such a points are there in the neighborhood. Then we say A comma B is the saddle point. So this is one example of saddle point. This figure says this one is for local maxima and this one is for local minima. Okay. Now one characterization for the local extrema is that if f is differentiable and f has local maxima or local minima at a point AB, then the partial derivative has to be 0 at that point. Fx at AB should be 0 and fy at AB should be 0. Okay, partial derivative has to be 0 if it has a local maxima or local minima. Now I will define a point called critical point. So critical point are the points which satisfies these relations. Del f at AB. So that means critical points are the points such that fx at AB equal to 0 and fy at AB is equal to 0. So suppose you are given a function and you are asking you to find a critical point. So what actually you wanted to do, you first find the partial derivative with respect to x and equate equal to 0, and again partial derivative with respect to y and equate equal to 0, and solve the system of equation. Then you will get a point A comma B. That are the points for corresponds to the critical point. That are called critical points. So all these 3 points are critical points, what we have already discussed. So critical points includes local maxima, local minima, and the saddle points. Okay. Now there is a characterization for local extrema. So that is called second derivative test. So you have to assume that the function f is continuous has continuous second derivative. Assume that f has continuous second derivative and AB is a critical point of f. Here the AB is a critical point of f and f has continuous second derivative in an open disk D with the with the center in AB. Okay. Now you look at this quantity. This is the called the discriminant. Then if this discriminant is positive and the second derivative with respect to f is with respect to x is also positive, then we say f of AB is a local minima. And again for the discriminant positive case, if this is second derivative is less than 0, then we have a local maxima. If the discriminant is less than 0 itself, then we say f of AB is a saddle point. If D is equal to 0, then we say the test is inconclusive. So I will give you a method to remember this. You don't need to remember this equation as it is. This is nothing but the determinant of the Hessian matrix. So let us look at the Hessian matrix. What is Hessian matrix? H is given by this one. Hessian matrix is H, that is the first component will be dou square f by dou x square AB, and the second is dou square f by dou x dou y at AB, and the other one is dou square f by dou x dou y at AB. So this is the Hessian matrix. Now you look at the determinant of the Hessian matrix. That is your D, discriminant. Determinant is discriminant. That is D is equal to dou square f by dou x square AB, dou square f by dou y square AB minus dou square f by dou x dou y AB whole square. That is the discriminant. Now you see what actually this first condition says. D is positive. So the determinant of this matrix is positive. And fx at AB also positive. That means the first pivot is also positive. This one is positive. And the determinant is also positive. So what actually says, H is a positive definite matrix, right? Positive definite matrix. That is actually the meaning. So if H is positive definite matrix, then f of AB is has at the point A comma B, f has local minimum. And the other case is the determinant has to be positive and the first pivot has to be less than 0. Then f of AB has f has local minima at AB. And if the determinant itself is less than 0, then it is a saddle point. If determinant is equal to 0, then we cannot conclude anything about this. The test is inconclusive. Okay. So these are the second derivative test for finding the saddle point and the local maxima, local minima. Now we will go for some previous problems. Okay. I think it is. Yeah. Previous year problems. Okay. So let us begin with some questions from I think it is in JAM 2016 or something. Okay, let us begin with this one. So this is the function given. F of xy is equal to x cube plus 2xy plus y cube. Now you wanted to find the saddle point of these functions. Has a saddle point at where? That is the question. So let us look at the what we have to find first. First we have to find the critical point. Then we wanted to check whether that is a saddle point or local minima or local maxima. So here you need to find out the saddle point. Okay, so how do you find the critical point? You will take the partial derivative with respect to x first. So you look at fx. What is fx? Fx at xy. What is that? It is 3x square plus 2y, right? Okay. Now again you have fy. What is that? Fy is 2x plus 3y square. Now both you have to equate to 0, right? So you have a system of equation. 3x square plus 2y is equal to 0. And 2x plus 3y square is equal to 0. Now you have to solve x and y using this equation. That's all. So from first equation, what you can write? 2y is equal to minus 3x square. So you can write y is equal to minus 3 by 2 x square. This is from the first equation. And the second equation, you can write 3y square is equal to minus 2x, or the y square is equal to minus 2 by 3x. Now you substitute this one into here. Here you have y equal to minus 3 by 2 x square. So that you substitute here, what you will get? 9 by 4 x raised to 4. That will be equal to minus 2 by 3 x. Okay. Then you will get x raised to 4 is minus 8 by 27 x. So there are two possibilities. Either x is equal to 0 or x is equal to, or x cube is equal to minus 8 by 27. So if x is not equal to 0, you can divide this. So you get x cube is equal to minus 8 by 27. So this implies x is equal to minus 2 by 3. Okay, so there are two possibilities, x is equal to 0 or x is equal to minus 2 by 3. So if x is equal to 0, what is your y? So you can substitute here, right? X is equal to 0, you can substitute in this equation, then y you again 0 you will get. So the first point is 0, 0. You have a point 0, 0. The critical point. Another point is, and you have x is minus 2 by 3, and y what you will get in this equation if you substitute, y you will get, here I will write, x is minus 2 by 3, then y is equal to minus 3 by 2 into x square, right? So you have 4 by 9. Again you will get a minus 2 by 3. Okay. So you have another point, minus 2 by 3, minus 2 by 3. So these are the 2 points, 2 critical points. They are critical, sorry. Points. They are 0, 0 and minus 2 by 3, minus 2 by 3. Now you wanted to check which point is the saddle point. Okay. So to look at the saddle point, you first go for the discriminant. Is D. D is fxx. So I will look at the point 0, 0. So you can write it as in generally fx at AB, fyy at AB minus fxy at AB whole square, right? So you look at the second derivative. What is the second derivative? So you have fx is this one. Again, you take the derivative with respect to x. What you will get? You get a 6x, right? So fxx is 6x. Fxx is 6x. And what about fyy? That you will get 6y. Again, you will get a fyy is 6y. What about fxy? Fxy you will get in this equation, fxy if you take with respect to y you have to take, so you will get 2. Okay. Now you look at about the point 0, 0. So you first substitute the point 0, 0. So fx at 0, 0, what you will get? 0, because 6x. So you have 0, 0 into fy at 0, 0, that is also 0, 0 into 0 minus fxy, that is 2. So fxy at 0, 0 is 2 itself. So its square is 4. So you get a minus 4. Ultimately D you will get as minus 4. So this is less than 0. Then you can conclude that 0, 0 is a saddle point. Similarly, you can look at the point minus 2 by 3, minus 2 by 3. Same way, just substitute here and compute it. You will get it is D is equal to 0 there. So you cannot give any conclusion with about minus 2 by 3, minus 2 by 3. So the saddle point is nothing but 0, 0. That is the saddle point. So has a saddle point at 0, 0. This is the answer. Is that clear? Any doubt?
Clear, sir.
Okay. So we will go for another question. This is a GATE 2021 question. Here you have a function f from R2 to R. It's a differentiable function. And du f at 0, 0 and dv f at 0, 0 be the directional derivative. It is given. And u is given by this one, 1 by root 205, 2 by root 25, and v is this one. And both the directional derivative are given. The question is to is that you have to find this fx at 0, 0 plus fy at 0, 0. So what is the directional derivative? You can use the formula here because f is a differentiable function. So what is du f at 0, 0? Since f is differentiable, you can directly use the formula. Du f at 0, 0 is del f at 0, 0 dot u. Okay. So here u is 1 by root 25, 2 by root 25. Here the given vector is a unity vector. That is already mentioned here in this question itself. It is unity vector. Sometimes they will not give the unity vector. So in that cases, you have to make it as a unity vector. How you will make it as a unity vector? You just divide throughout by the norm of the vector. That's all. So, but in this cases, in unity vector itself, they have given. Okay. So du of f at 0, 0 is del f at 0, 0 dot u. Now, what is del f at 0, 0? That is fx at 0, 0, fy at 0, 0 dot u. U is 1 by root 5, 2 by root 5. Okay, so you will get a one equation. Fx 0, 0 plus 2 times fy 0, 0 divided by root 5. So this is one equation that is given as root 5, right? Du f at 0, 0 is given as root 5. Here it is given. Okay. So one equation you got. So you can rewrite it as fx at 0, 0 plus 2 fy at 0, 0 is 5. Okay. Now again directional derivative in the direction of v is given. What is that? Again it is dvf at 0, 0. That is nothing but fx 0, 0 fy 0, 0 dot 1 by root 2 minus 1 by root 2. Okay. 1 by root 2 minus 1 by root 2. So this will be fx 0, 0 minus fy 0, 0 by root 2. Okay. So that is given as equal to root 2. So again you can solve it. Fx 0, 0 minus fy 0, 0 equal to 2. So you have two equations. This is 1 and this is 2. So this is a system of equation. Then now you can solve how it is, right? So you will get, you just subtract it, fx will cancel, then it will be 3 times fy 0, 0. That is you get 3, right? 1 minus 2 will give 1 minus 2. So you have fy at 0, 0 is 1. Since fy at 0, 0 is 1, what will be your fx? That will be 3, right? Fy at 0, 0 is 1. You can substitute in 2. It is 1. So fx at 0, 0 is 2. So ultimately your answer is what? You want to find the sum, right? Sum is 1 plus 2 is 3. So your answer is 3. You understand?
Yes, sir.
Yes.
Yeah. So this formula we are able to use because f is differentiable. That you have to remember, right? Here f is given as differentiable. That is why we are able to use this formula. Otherwise, you have to use the direct formula to compute the directional derivative. Yeah. So now look at another question. So I think you guys can do this thing if you can. I will give you what is time now? 5 minutes or 4 minutes. You can just try this. That will be better. Some of them can try and tell me the answer. The same only, the directional derivative of f at 0, 0 in the direction of this.
Sir, is it 2.6?
1 minute. 2.6. No. 2.6. Yeah, is 1 minute. Yeah, yes, 2.6.
Yes, sir. Yes, sir.
Anyone else? I'm able to see where.
Sir, sound is not clear, sir.
I'm not seeing a response. Got it? 1%
Hello?
study this that.
Yes, sir.
Am I
No, sir.
No, sir, some net issues is there.
No, sir. Net is vibrating, sir. Your voice is vibrating.
Am I audible now?
Yes, sir. Yes,
Yes,
sir.
Yeah,
But not clear, sir.
Yeah, okay. Anyone else got this 10.6? 1% said 2.6. That was I heard.
Yes, sir, it's 2.6.
Yes, sir.
Yeah, okay, fine. So, okay, I can do it, but I think you tried. That will for a question. Same using the definition of directional. I already show one example how to find the directional derivative. Okay. So let us look at another question. This is a GATE 2010 question. So this question is this one. Given f of x y is this, and then the value of k for which f of x y is continuous at 0. So you have to find the value of k so that f of x y is continuous at 0, 0. So for what value it will be continuous? There is a question. You have to limit y tending to 0, 0 f of x and equate it to k, and you should solve it. So let us do that. There is a alternative method I will use. This is I will use these parameters form and so doing directly that will be easy. So do this.
sir, screen is not
Sir,
visible.
screen is not coming, sir.
Screen is not coming.
yeah,
Yes,
Mahesh,
sir.
the screen has gone.
Oh, 1 minute. I think it's some net problem. Just a minute. Okay. I will share once more. Okay. I will stop sharing and do it. What happened to this one? Oh, internet has gone. I don't know.
Okay, your voice is coming.
1 minute. 1 minute. I don't know what happened.
Or if you want, you can try rejoining.
Yeah. Okay. Okay. That will be better, I think.
Yes. Yes, Mahesh. You are unmuted now. Okay, you are muted. Please unmute.
Yeah. Something is coming there in share. No. I am trying to share, but it's not getting. I don't know what happened. Okay, maybe some. Okay.
It's not coming so far. Yeah. Yes, now it is okay.
Okay, fine.
Yes.
Yeah. Yeah. Okay. 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 So we have to do this question. Okay. Yeah. Limit. So we wanted to find the value of k for which f of xy is continuous at a 0, 0. So you look at the thing limit xy tending to 0, 0 f of xy. That is what we wanted to find. Here f of xy is xy divided by x square plus y square whole raised to 5 by 2 1 minus cos of x square plus y square. So to do this one, I will use the parameterization. That will be easy. So what I am doing is I take the parameterization. X is equal to r cos theta, y is equal to r sin theta. This is the parameterization I am doing. Then this equation you can rewrite as f of r theta is equal to what? F of r comma theta. That will be equal to here in the numerator you will get r square cos theta sin theta, cos theta sin theta, and denominator you have r square raised to 5 by 2, and here you have 1 minus cos of r square. So this is the thing you have. Okay, now xy tending to 0, 0 implies what? Xy is tending to 0, 0 means
R tends to 0.
r tends to 0. Okay, this is implies this one, right? Okay, now you need to find limit r tending to 0 f of r theta. So this you can rewrite this. Here you have r raised to 5 is there. This 2 will cancel. R raised to 5 is there. Here r square is there. So that I can rearrange, and it will be limit r tending to 0 cos theta sin theta divided. Here I will write it as this one, 1 minus cos of r square by r cube. This is the way you have. Okay. Now limit r tends to 0. This quantity you have to find. So again, this one is L'Hopital's rule. You can apply. It will be 0 by 0 form. Cos 0 is 1. So numerator you have 0. Denominator also you have 0. You have to take the derivative with respect to r. So what you will get? So cos theta sin theta you can take outside. There is no r inside. So there is the limit r tending to 0. Here you take the derivative. What you will get? The numerator you have sine of r square into 2r. Denominator you have 3r square. So r will cancel. Here also r cancel. So you have remaining one more r. So you can take 2 by 3 outside, and yeah, 2 by 3 outside. So what you will get? Cos theta sin theta 2 by 3 limit r tending to 0 sine of r square by r, again 0 by 0 form. You can take the derivative. What you will get? Cos theta sin theta 2 by 3. This is cos of r square into 2r by r. Sorry, by r is not there. This is 1 derivative I have to take, right? 1. So again limit r tending to 0 is there. So this numerator will be 2r into cos of r. That it goes to 0, right? Yeah. So ultimately you got 0. So k will be 0. So in order to have continuity, k has to be 0. So this is the first option is right. Do you understand this?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, okay. Now we will see another question. F is given by this one. F of xy is equal to square root of x square plus y square into sine of y square by x, x not equal to 0, and 0 if x equal to 0. So consider the following statement. The first statement says f is continuous at 0, 0, but not differentiable at 0, 0. And the second statement says the directional derivative exists in the direction of every unit vector u in R2. So you have to find continuity and the same. So as in the previous case, again I will do this using this parameterized form. Again you can write f of r theta. What is f of r theta here? F of r theta is x is r cos theta. I will write it here. X is r cos theta. Y is r sin theta. So f of r theta, you will get it as root of r square. So it is r. Sine of y square is r square sin square theta by x is r cos theta. Okay. So what is this one? R into sine of r tan theta sin theta. You can say tan theta sin theta, whatever it is, doesn't matter. Okay. Now what you can say about this one? Limit r tending to 0 f of r theta, where it goes. What is this quantity?
0, 0.
0, because you can take modulus, the sign is bounded by 1. So then you can use the sandwich, right? Both left and right will goes to 0. So the intermediate one also goes to 0. So this will be 0. Okay. Now you wanted to look at the differentiability. So first you have to take the partial derivative with respect to x at 0, 0 and y with respect to y at 0, 0. So first you consider the partial derivative with respect to x. So what is fx at 0, 0 you look at, and fy at 0, 0, both you consider. So suppose that derivative exists. I have already mentioned that thing. Suppose the derivative exists, what should be the derivative? Suppose the derivative exists, then there exists a pair alpha beta satisfying that relation that I have in the definition I told. So if such a derivative exists, then alpha has to be what? Fx at 0, 0. And the beta has to be fy at 0, 0. So the corresponding linear map what you are looking is nothing but L, that is fx at 0, 0 h plus fy at 0, 0. Okay. So this has to be your derivative. If it exists, this has to be this one. So first you look at whether fx at 0, 0 exists and fy at 0, 0 exists. Then compute L. Then if you can check whether the function is differentiable or not. So let us do first this one, fx at 0, 0. What is that? Limit h tending to 0, f of h0 minus f of 0, 0 by h. Correct? So what is f of h0? Here y is 0. So in this equation, if you put sine of y square by x is there, so that will be 0, right? So f of h0 is 0, f of 0, 0 is 0. So ultimately this one is 0. Okay. Now what about fy at 0, 0? That is limit h tending to 0, f of 0h minus 0, 0 by h. What is f of 0h? Here x is 0, right? Where x is 0, so f of 0h is 0 only. Then this is also 0. So you got fx at 0, 0 is 0, fy at 0, 0 is 0. So if it is differentiable, the derivative has to be 0 only. So now you wanted to look at whether the function is differentiable or not. How you will look at? You have to use the definition of derivative. What actually it says? Limit function is differentiable if limit hk tending to 0 0 f of hk minus f of 0 0 minus alpha h minus beta k divided by root of h square plus k square. It should exist. That is the meaning, right? It should be equal to 0. That is the definition of derivative, and this quantity is giving the derivative. Here derivative is alpha beta. So if such alpha beta existing, alpha and beta are fx at 0 0 and fy at 0 0. So we have already find fx at 0 0 is 0, fy at 0 0 is 0. So alpha and beta are 0, and f of 0 0 is what? F of 0 0 by equation, that is also 0. So the only thing we wanted to look at is whether this limit, which limit hk tending to 0 0 f of hk by root of h square k square, whether this is 0. This is the question. So if it is 0, then the derivative exists. Derivative is 0 itself. So that is the problem. So what is f of hk? F of hk you substitute here, you will get f of hk is square root of h square plus k square sine of k square by h divided by root of h square. So that is the one. This is the one is f of hk. Sorry, this is f of hk. Now you wanted to look at f of hk by root of h square plus k square. So that will be sine of k square by h. Now you wanted to look at whether this limit exists. If so, you need to look at limit hk tending to 0 0 sine of k square by h, whether this exists or not. That is the question. Okay. So what you can say about this, whether this limit exists or not? Sine of k square by h.
Does not exist.
Yeah, this does not exist. How? Why?
If we take the curve k square equal to h and goes along this curve to 0, 0, then k square equal to mh. Actually, if we take k square equal to mh, then limit depends on m.
K square is equal to mh. Yeah. Yes. Then it depends on the m. Correct. Fine. Sine of m you will get. So it depends on the m. So what you have to take is if you consider the curve k square is equal to mh. Along this curve, if you approach, then what you will get? This limit will be limit hk tending to 0 0 sine of m you will get. mh by hh will cancel, so sine of m. So that is sine of m. That depending on m. So if you take, if you are varying m, you will get different value. That's all. So this limit does not exist.
Hello, sir.
Yeah, ask. Yeah, tell me.
Sir, my question was, if we put a is equal to r cos theta, k equal to r sin theta, then also the limit equals to 0. If we approach r tends to 0.
Yeah, r tends to 0. Which one goes to 0? I didn't understand. F of r theta, you are saying. No, I didn't get it.
Sir, my question was, if we put h equal to r cos theta and k equal to r sin theta. Yes.
Yeah, h equal to r cos theta, k equal to r sin theta. Okay.
In polar coordinate.
Okay.
Then also limit is 0. Then how can we say that limit exists? We can see that if we put k square equal to mh, then limit does not exist. But if we transform it into polar coordinates, then limit is equals to 0.
No.
Previously you solved one problem.
Yeah. That I understood. Your question I understood. Suppose you take h equal to r cos theta and k is equal to r sin theta, right? Then what you will get, sine of sine of r r square sin theta by r cos theta. Fine. This is sine of r tan theta. Okay. Now your problem is what? R tending to
If
0.
Yes,
Yeah.
sir.
Okay.
Then also the limit is 0.
No. You here. You suppose you are taking. So what actually your idea here? You have to approach 0, 0, right? So suppose you are. This is the point, and you wanted to approach this point 0, 0. So different curve we will look at. So suppose this is the one. So here the theta is pi by 2. If you take, what value you will get? So theta. So it actually, once you put 1 theta along that value, you will get one value. If you give another theta, you will get another value. That is what I want. You understand? Suppose you take theta is equal to pi by 2. Then what actually your pi by 2 value give? If you put pi by 2, this will be.
So then also the value would be 0 if we vary theta also.
It is not correct, right? It cannot be.
Sir, previously you solved one problem just by putting r cos theta, r sin theta.
Yes,
That's
yes.
why I asked here.
Yeah, there is whatever this question, right? If you put any theta, this sin theta cos theta will be independent of this function sine of r. So here you see this question only you asked. Here you can take this sin theta cos theta outside because that is not depending on these functions. Only the limit is depending on these values. So what actually we are doing is we are approaching 0 with a different path. Different path means you are giving different value for theta. So all such whatever the theta you give, this limit is only depending on r. But in this case, it is not like that. The inside quantity will affect. That is the difference. In this case, this theta's effect also will come there. There it is not like that. Do you understand the point?
Yes.
That is why this problem is coming. So you have to give appropriate theta so that it will get a different value. So
Sir, whatever value we give theta, tan theta will be a real number. Okay.
Yeah.
And when we approach r tends to 0, then obviously add 0 into some real number, that will obviously be 0. Whatever we take theta, the limit is 0 here.
What
Actually,
about the tan pi by 2? That is in going to infinity, right?
In that direction, limit does not exist.
Yeah, tan pi by 2, if you take, the limit does not exist.
Yes,
Suppose I am approaching 0 along theta equal to pi by 2. That curve, what happened? Limit does not exist, right?
Yes, sir.
Yeah.
Sir, one question I also had: if along all the path, this is basically a circular helix, right?
What?
R cos theta. This path is basically a circular helix.
Yeah. Yes. Correct. Yeah.
So
Circular.
if along this path for all theta and for all r, if the limit exists, then can we say that the limit exists in all the direction?
Yeah, of course. Why? You are taking any uh, uh, a point 0, 0, you are approaching that point, right? Through any
Yes.
direction, any direction. So you are, you suppose you are taking some curve. So approaching means you have to take a smooth curve, right? So you
Okay.
let us look at some. This is the point. So you wanted to some curve you are having. So you wanted to approach along this curve means what? This is you have to look at very close that theta that correspondingly you can look at this point on the circle and you can approach, right? What is the problem there? Every path will consider by this arc cos theta, right?
Yes, yes, sir. Okay,
Yeah,
I got it.
yeah. Okay. So what is the next question? We will go for.
Sir.
Sorry,
Sir.
sorry. Yeah, okay, okay. Sorry. I have what we got is the first one is correct. Right? F is continuous at 0, 0 and is not differentiable at 0, 0. Is that correct? That much only we got. Hello? Hello?
Yes, sir.
Yes, sir. Yes, sir. Continue, sir.
Yeah. Okay, now we will go for the second question. The directional derivative exists at 0, 0 in any direction. So let me look at the directional derivative. So I don't have space here. Okay, then I will write it here. So I'm writing here. I don't have space. Okay. So you wanted to find the directional derivative. It is 0, 0. So that is duf at 0, 0. That is limit t tending to 0 f of tu1 tu2 minus f of 0, 0 by t. Okay. So f of tu1 tu2. What is that? If you given this quantity there, f of 0, 0 is 0 and f of tu1 what you will get? From here it will be, this is equal to limit t tending to 0. So t square, you have a x square plus y square, tu1 square plus tu2 square. So t square into u1 square plus u2 square will come. u1 square plus u2 square is 1. So it is root of t square in t square you will get into u1 square plus u2 square is 1. Then sine of y is t square u2 and t square u2 by tu1 by t is there. Okay. So then again you have this is sine t u2 by u1. So t will cancel. Here you have mod t will come. Root of t square is mod t. So this is limit t tending to 0 mod t by t sine of tu2 by u1. Okay. So again t tending to 0, what happens? This quantity is going to 0, right? Yeah. So or otherwise you can say, if you consider this together, you will get a u2 by u1 by u2. What about the limit t tending to 0? Sine of t u2 by u1 divided by t you can take. You just 2 and subtract by u1. Then you have here also u2 by u1 will be there. Then this quantity is going to 1 as t tending to 0. So ultimately you will get a u2 by u1. But mod t is there. As t tending to 0, mod t is going to 0. So finally you will get 0. Got it? Is that clear?
Okay.
Yes, sir.
Okay. Okay. Pardon, I didn't.
Yes, sir. Yes, sir.
Okay. So you got du of f at 0, 0 is 0. It exists in all directions. So the directional derivative of f at 0, 0 exists in the direction of every unity vector u belongs to. So the q is true, p is also true. So both the statements are true. That is your answer.
Sir, in previous question, sir.
Yeah, this question. Huh?
Yeah, sir. This question, no, sir.
Yeah.
उसके अगले वाला सर. Sir, for the as the sufficient condition of differentiability. Hello.
Yeah, sufficient condition for the differentiability. Sufficient.
Sir, fxy at 0, 0, and one of them should be continuous. Hello.
Yes, fine. One of them should be continuous. Yeah.
Continuous. Sir, here we get fx 0, 0 is equal to 0, and fy is, how can you show that this is discontinuous, sir? This is a continuous function.
No, I am not. You are finding derivative at only one point. Continuity
Yes.
and everything, if you wanted to discuss, you have to discuss in a small neighborhood.
Yes, sir.
So you have to find the fx at a comma b for every a comma b belongs to the small neighborhood of 0, 0.
Yes,
Again, you have to find the fy at a comma b for the small neighborhood of 0, 0. Then only you can talk about the continuity. I am not using that result.
Yes, sir.
I'm not using that result. What I did is, suppose f is differentiable. Suppose f is differentiable. What you can say about the derivative? So what is the definition says? Better I will go back. Okay, I don't know. Okay. What is the definition says? F is differentiable means there exists some alpha beta belongings to R2 such that this relation holds. Limit h comma k tending to 0, 0 f of or a comma b, doesn't matter, f of a plus h b plus k minus f of a comma b minus alpha h minus beta k divided by square root of h square plus k square. This should be 0. This ultimately should be 0. That is the definition says, right? There should exist some alpha comma b satisfying this. Suppose it is differentiable. What are these alpha and beta? Alpha should be fx at
AB.
b, and the beta is fy at ab. So first what I find is fx at 0, 0 I find, fy at 0, 0 I find. So if it is differentiable, I am assuming, I am saying that suppose it is differentiable, then your derivative should be L, that is your alpha h plus beta k. That quantity should be 0 there, because I got alpha is 0. Alpha is fx at 0, 0. I found that alpha is 0, and beta also I found that 0, right? So anyway, if it is differentiable, I don't know whether it is differentiable or not, derivative has to be 0. There is no other choice for derivative. So I put that value here. I put 0 here. Then another value is f of 0, 0. That also I put here, f of 0, 0. That is also 0 from the definition of function. Then these two quantity I got 0. So the only thing remaining is this much. So I need to prove that this limit goes to 0. Then I can conclude that function is differentiable. If it is not going to 0, I can say that the function is not differentiable. You understand?
Yes, sir.
So only thing I need to look at this limit and check whether the limit is going to 0 or not. Then I found that this limit is not going to 0 or is not existing in fact. That is what we did. You understand that?
Yes, sir. Yes, sir.
Yeah.
I understand.
Yeah, fine. So what is your answer is this one. Both P and Q are true. Okay. So now we will go for another question. This is again for the local maxima and the saddle point. So if you want, I can do one more question, one different question I will do, that will be better. This is the same type of question what we have already seen, local maxima and saddle point. Okay. Okay, let us look at this question. This is a CSIR question. Okay, so we have a function given by f of xy is equal to x to the power greatest integer of y. This is the function given. This is the greatest integer part, okay, of y. This is the function is given. Now the question is about the continuity of f and continuity of this function going to f of xy. These are the questions. Okay, let us look at this function first. So first we wanted to observe what are the how functions behave in a domain. Okay, so let us draw the figure here. So this is the domain. R2 is the domain. Now suppose your y is varying from 0 to 1. So I'm not including 1. So I'm just thing like this. Okay. So in this region, what should be your function? So your function is f of xy is, can someone tell me what is the function? To the power integer y. This is the function. So what should be the function? So this is the domain I am looking. I draw the domain here. So suppose your x is coming from here in this particular portion. So what should be your f? What is f of x? Yeah, yes. So in this region, f of xy is 1. Is that okay? Because greatest integer of everything coming from here is 0. Suppose you take any point here, the greatest integer will be 0. Okay. Now if I look at the other region, 2 I fix here. I just not including this boundary, but I included this boundary. This boundary I included. The other one not included. So what about this region? What should be the function here? How the function look like here? F of xy is equal to
X.
Yeah, x. Good. Okay, again for this region, what happens? This boundary I included, but this boundary I am not including. 3. This is not including, but this boundary I am including. What about this region function? How it is look like?
X square.
Yeah, yes. F of xy is x square, and so on. Okay, fine. Now the first question is, f is continuous on R2. So that means f is continuous everywhere. That is the thing. So what you say the answer? Can anyone tell me the answer? From this figure you can easily observe. Is that continuous everywhere on the domain? Can you give me some point it is not continuous?
Yeah, in the line y equals to 2, it's not continuous.
Yeah, this line it is not continuous. Y equal to 2, it is not continuous. Or you can give
at any integer, it is not continuous.
Any integer. What about 1? This point?
That is continuous.
Yeah, it is continuous, right? Because everywhere it is 1, and here right side also it is f of x equal to x. So you will get 1 only. But if you take some point here, for example, I may give 1 point 2,2 if you take. Suppose you are approaching along some curve. Okay, what about the values here you will get? What about from the above portion, what you will get the value? Because I am taking 2,2 from the above portion I am approaching. In this region, your function is x square. So you will get 4, right? The limiting case, you will get a 4. Along this curve I am doing. So from the above you are coming, then you will get, I may write it as a limit xy tending to, it is not a proper notation, just plus I will put. And then f of xy is, you will get a 4, right? Yeah. Then what about from below, if you coming, what you will get? Here below, yeah, yes. So this is not a proper notation. I just, for the simplicity, I put, that's all. Okay, 2. So you will get different values, right? From the above you will get 4, and below you will get 2. So it is not continuous at this particular point. So likewise, you can find a lot of points here. The function is not continuous. You understand?
Yes, sir.
Yeah, it is someone told it is not continuous at any integer. That is not correct. If you look at 1, 0, or there you can find the continuity. 1, at least in this point you can find the continuity. 1. This point you can find the continuity. Yeah. Okay. Okay, so this function is continuous on R2 is wrong. So what about the second one? For every y belongs to R, x going to f of xy is continuous on R minus 0. Is that correct? So what you have to do? You fix one y. Fix some y. Then you look at the function x going to f of xy. Is that continuous? Hello?
Not for every y, sir.
No. Here you first fix one y, then you look at the function x going to f of xy. Suppose you take y is equal to 1. What about your function x going to f of xy? Suppose your x is y is 1. What is your function then?
It will be continuous.
Yeah.
X,
Suppose your y is 1. You will get x going to f of xy. You have to look at x comma 1. You have to look at what is that? This is x itself, right? X power integer 1 means 1 only. So x itself. Suppose you take x is equal to y is equal to some minus 1. What you will get? You take y is equal to minus 1. In that cases, again you have x going to f of x comma minus 1. That is x to the power minus 1 will come. That is 1 by x. But it is again continuous. Our domain is r minus 0. We are talking about r minus 0 only. You understand? Is that clear? So you fix each y and look at these functions. So only possibility is that y can be negative integer. Then it will come below the x will come below the it will be something like a fraction. Then in that cases again it is continuous because we are talking the domain on r minus 0. We are not talking on the entire r. That is the thing you have to point out there. So what you finally you will get integer only here. You fix y, so each y you will get integer, but that integer can be negative, but it will come below the thing. So it will be something like 1 by x or 1 by x square. Such a function can be come there, but we are talking continuity on r minus 0, not on the entire domain. Is that correct? So
Yes,
every every y it is continuous. So what about the third one?
So this is not continuous for every y. Sorry, for every x.
Yeah, why?
If we take x equal to 2 and then integral point of y, it is not continuous.
Yeah, yes, correct. If you take x is equal to 2, in the first region you will get 1, and the second region you will get 2 square. So what is your, suppose you take x is equal to 2, what is your function? You can easily put here, x is equal to 2. So what is your function here in this region? In this region it is 1 only. What about here? You will get a 2. The entire region you will get a 2. The entire region you will get a 4. Correct?
Yes, sir.
Yeah. So it is not continuous on these lines. On these lines it is not continuous. Okay. And what about the fourth option? F is continuous at no point of R2. Is that correct?
No, because one.
Yeah, each portion it is continuous, right? Each region it is continuous. 0, 1 region that is continuous. 1, 2 also it is continuous. So its continuity is saying continuous at any point. That is not correct. Okay. So the option 2 is true. I have already marked this one is true. Option 2, right? Okay.
Hello, Mahesh.
Yeah.
Our time is almost over. If you want, we can go for one more problem. By that, we need some time for interaction as well.
Okay, fine. Okay, then I will give you a somebody can answer these questions. This is, I think, very simple one. Or which one of the following is true? Some of them.
Sir, A and B.
Yeah,
A
let
and
me.
D.
Okay, then the following. Okay, if f is differentiable, all the directional derivative. Okay, correct. What about the second one? What about second
Not,
one? Somebody told that this is correct. Is that correct?
No, sir. No, sir.
no,
Why?
No, sir.
Why?
because we solved last example under root of.
What we did, all directional derivative of x is 0, but we found one discontinuous function. It's not even
A and B.
differentiable. No, B is not correct.
A and D.
If the partial derivative of exist and are continuous in a disk center 0, then f is yes, correct. This is correct. This is correct, and this one is also correct. So these two are wrong. We have already discussed. Continuous function is you can. This one itself is wrong. Then how it can be true? Differentiable function has to be continuous, right? That is the first property. So you can find a discontinuous function in which all the directional derivative of x is 0, 0. So you can find a discontinuous function. Then there is a non-differentiable function. All directional derivative of x exist. So these two are wrong, and these two are correct. Okay? Is that clear? Any doubt? Hello? Is that clear?
Yes, sir.
Yes, sir.
Okay. Okay, I will stop here then. Some more questions are there. If there are type of repeating type of questions, so you can just do the questions. I think no, there is.
I think we can share that with them. That
Okay.
PDF with that, if possible.
Yeah.
Okay, thank you, Mahesh, for being with us and presenting the basic ideas related with functions of several variables and many tricks for helping the students to solve the problems from the area of functions of several variables. Mahesh, you can off the presentation, I think.
Okay.
Sir.
Now it is time for interaction. Students, you can ask any questions or any comments.
Sir, I have a question regarding uniform continuity. If in single variable case, if f maps open AB to R is continuous, then if the limit at A and B of f exists, then we can say that f is uniform continuous.
Yeah, same way you can do for here also. You can, but that should be on a rectangle. Open rectangle if you can.
If f maps D to R, where D is a subset of Rn, then if the limit of f exists at all limit points of D, then can you say that the f is uniform?
Yeah, you can extend continuously on the if it has to be a bounded domain, first of all, D. Then if you included all the limit point, it becomes the composite. Then continuous function on a composite is uniformly continuous, right?
Yes.
Yeah. If you can rewrite it on the composite. So it has to be a bounded domain. That is the same thing you are doing in the single variable case also. You are extending on the composite. It is not allowed for the unbounded set. The theory what you said is only for some open interval cases, right?
Yes, bounded.
Yeah, bounded set only.
So we are extending f to the compact set, and that function is continuous. So this is uniform continuous.
Yeah, you can
therefore,
say
this f is a restriction map of that function. So f will also be uniform.
Also uniformly continuous.
Yeah,
Correct.
okay.
Correct.
Okay.
Yeah.
Okay, thank you, Tanmay. Others?
Hi, sir. I am Geetu. I am a third year BSc student. Your class was very effective and informative. The topics you taught were very clear to us. Thank you, sir, for coming and giving such a wonderful session. We are expecting more classes from you. Thank you, sir.
Okay, thank you, Geetu.
Hello, sir.
Yes.
Am I audible?
Yeah, yes.
I'm a third year BSc student. My name is Satira. Your class was very informative and the way you explained the points like the continuity and how it's related to partial derivatives and stuff. It was very useful and the questions were also very good. Thank you, sir, for such a class. We expect more classes from you in the future. Thank you, sir.
Okay,
thank you, Atira. Yes.
Sir, my name is Kavya. I'm from Atomo College, Undittara. The class was really useful for us and you have explained everything clearly and neatly and the concept was also clear for us. Thank you for coming and having such a wonderful class. Thank you so much.
Okay, thank you, Kavya.
Sir?
Yeah.
Yes.
Sir, your class was really nice. Sir, I would like to ask you something a little different from the topic you took. Can you please tell me what are the applications of these topics, functions of two variables and the partial derivative, everything in our real life? Calculus has got so many applications. So similarly, the applications.
Real life. Okay, if you are
Yes,
looking all the partial, basically. So I can tell you, I will give you one example. That will be better, I think. So this is the one I heard from my teachers, or somebody told me previously. Suppose we are, since I am working in space related, I will tell about that. So suppose you are sending some satellite or something into studying about or some orbit. So it will be traveling along some particular path only, right? That is the important. We will always look at that. There should be a trajectory. Along the trajectory only it has to move. But sometimes this particle can be deviated from the trajectory. Then it will deviate. It will lose the contact from here. People are doing all the things from here only. So that contact will lose. So what we will do, we will send a controller from here to there, and we will control it and come back to this original orbit. So these controller and everything will turn out to be mathematically a partial differential equation. So those things we can, these theories only using there to solve these partial differential equation and all. That is the application I can tell you. I don't know whether very specific what you are expecting.
Okay, sir.
Okay.
Thank you.
Thank you.
It was just a matter of curiosity, sir.
Okay. There's a lot of applications are there. These engineering people, they are doing basically with these things only. Yeah.
Yes, others.
Hello, sir.
If you have, yes.
Yeah.
I am TT and I am a M.Sc first year student.
Yeah.
And your session is really good for our competitive exams. And it was fun. And also thank to sir for arranging such beautiful session every week. Thank you, sir. Thank you so much.
Thank you, Titi. Any others? If you have anything, yes.
Hi sir, I am Namida Eldo, completed BSc Mathematics. Your class was very understandable and it's very informative. Thank you so much for your class, sir. It's very clear.
Okay, thank you.
Thank you, Namita. If you have anything to ask, any doubt regarding the topics discussed or anything regarding about the preparations, you can ask him. Okay. So, is there anyone? Otherwise, we will wind up here. Okay. Thank you, Mahesh, for being with us.
Yeah.
Thank you, everyone. So, I will contact you, Mahesh. Please share the PDF that can be shared to the students.
Okay.
Okay. Thank you.
Sir,
Thank you, everyone.
sir, may we get the
Yeah.
information about the class next day?
That will be shared in our WhatsApp groups.
Actually, I am not in your WhatsApp group. If you join me,
Okay, you can just WhatsApp me.
your information, contact number.
Yeah, I will put it in the chat box.
Okay.
Sir, suggest some good books for this several variable calculus.
Yeah, I suggested two books. So first, that is a course on multivariable calculus by Limai and Gropade. The another one I suggest is that calculus on manifold by Spivak. And if you are more interested, if you can, there are some books. Rudin also very good only. Rudin, some portions are there. Calculus functions of several variable portion is there in Rudin, mathematical analysis. And some other book, if you look at any manifold books, like smooth manifold, introduction to smooth manifolds by John M. Lee, all those books having some ideas, but it will be like abstract only. But for problem oriented approach and all, I suggest this one is the better. This Gropade and Limai, that one is very, very good. For a lot of concepts they are discussing. Most of the examples what I took from there only. You can look at that. That is a very nice book for at least for the competitive exam point of view.
Okay, sir. Thank you.
Okay.
Any others? Any queries?
Sir.
Yes.
So in CSIR NET, what will be a good percentage to get a good rank, approximately? And the important portions.
Important portions, I think you have to basically for me what I did is I will tell what I did. I studied only basic courses like analysis, algebra, and linear algebra, complex analysis. This much only I did for clearing those exams, and some multivariable calculus also I did. This much only. I have not done anything from applied subject, but and I got a reasonably good mark. I feel I got about 130 or 135 marks, something I got. I suggest you have to concentrate at least linear algebra and real analysis. Both those two subjects are very important for this CSIR. They usually ask more about 120 questions from that itself. Then if you study some little bit algebra and complex analysis, you can surely get a good mark. I don't know how much percentage you want that. I don't know how. Yeah, people are getting about 170, 180 marks every year. Very good rank. They are getting first rank. I think last time also I 180 or 170 or something they got. So that much you have to score for getting very good rank. So for that, if you are expecting that much topic, you have to read all the topic. For me, what I did is I concentrated only some specific topic like analysis, algebra, complex analysis. That only I did.
Yeah, thank you very much, sir.
Yeah, Tanmay, you can concentrate on core areas, and while you get time, you can go for the others also. That will definitely help you to get more marks, and your rank will be get improved.
Yeah, thank you, sir.
Any others? Any queries? Okay. Okay, I think we can wind up here. Okay. So all the very best, students, all the very best for your preparations. And once again, I thank Mahesh for being with us. Thank you, everyone.
Thanks. Thank you, sir. Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.